Hello again, I'm Damla Senol Cali, and thank you so much for joining to my talk. I'm a staff software engineer focusing on hardware acceleration at Bionanogenomics, and I received my PhD degree from Carnegie Mellon last year. And today I will be presenting one of my PhD work, GenASM, which is published at Micro 2020. So we all know that genome sequencing plays a pivotal role in areas such as personalized medicine, outbreak tracing like COVID-19, and the understanding of evolution. And modern genome sequencing machines extract small randomized fragments of the original DNA sequence, which we call reads. And state-of-the-art sequencing machines produce either short reads or long reads. And again, as we know, read mapping is one of the first key steps in genome sequence analysis, where we take each read, align it to one or more possible locations within the reference genome, and find the matches and differences between the read and the reference genome segment at that location. And since multiple steps of read mapping must account for the sequencing errors and for the differences caused by genetic variations, we need to perform approximate string matching. However, it is currently bottlenecked by the computational power and memory bandwidth limitations of existing systems. Our goal in this work is to design a fast and flexible framework for both short and long reads, which can accelerate multiple steps of genome sequence analysis. To this end, we propose GenASM. And we base GenASM on BiTAP, which is an ASM algorithm that uses only fast and simple bitwise operations, making it amenable to efficient hardware acceleration. And to our knowledge, GenASM is the first work that enhances and accelerates BiTAP. And we modify BiTAP to support long reads and to enable parallelization. And we also develop a novel BiTAP-compatible algorithm for traceback. And we co-design specialized hardware for both algorithms. GenASM is flexible and can be used to accelerate multiple use cases. And in this work, we evaluate 3 use cases in detail: read alignment, pre-alignment filtering, and edit distance calculation. And we find that for all the 3 use cases, GenASM is significantly more efficient in terms of both speed and power consumption than state-of-the-art software and hardware baselines. Okay, let's look at approximate string matching and the BiTAP algorithm in detail. As I introduced, when we are mapping the reads generated from the sequence genome, we have to take genetic variations and sequencing errors into consideration. And as we can see from this example, these errors and differences, which are known as edits, can take the form of deletions, substitutions, and insertions. And since multiple steps of read mapping must account for these errors, they must perform approximate string matching, or ASM. And approximate string matching is typically implemented as a dynamic programming-based algorithm, which has quadratic time and space complexity. Therefore, it is desirable to find lower complexity algorithms for ASM. And one candidate to replace DP-based algorithms for ASM is the BiTAP algorithm. So BiTAP uses only fast and simple bitwise operations to perform ASM, making it amenable to efficient hardware acceleration. And BiTAP tackles the problem of computing the minimum edit distance between a reference text, which can be a reference genome, and a pattern, which can be a query read, with a maximum of k number of errors. The algorithm has 2 steps. It starts with a pre-processing procedure where we generate one pattern bit mask for each character in the alphabet, which is ACGT in our scenario. And these pattern bit masks help us to represent the query pattern in a binary format. And the second step, which is the searching or edit distance calculation step, is the main step of the algorithm. And here we examine each text character one by using the pre-processed pattern bit mask from the previous step, status bit vectors, which are updated at each text iteration and hold the partial match information for the text characters examined so far, and bitwise operations. So I won't get into the details of the algorithm, but let me highlight 3 key properties of the algorithm. First, BiTAP iterates over each text character as the outer loop, and it iterates over each possible edit distance 1 to k as the inner loop. So when we have long error-prone reads, both of these loops need to iterate over very large numbers. And second, there is two-level data dependency in BiTAP. So first, there's an outer loop data dependency when computing deletion, substitution, and match bit vectors, as they require old R bit vectors, which are coming from previous text iteration. Also, there's an inner loop data dependency when computing insertion bit vector, as it requires RD-1, which is coming from previous inner loop iteration. And third, BiTAP generates these four intermediate bit vectors: deletion, substitution, insertion, and match, but they are not stored and processed with a traceback step to find the optimal alignment. So we find that BiTAP has 5 limitations that hinder its applicability and efficient hardware acceleration for genome sequence analysis. We have already covered the first 2 algorithmic limitations, and we find one more algorithmic limitation, which is no support for long reads. In BiTAP, the query length, so the read length, is limited by the word size of the machine running the algorithm, because each bit vector has a length equal to the length of the pattern, and we perform the bitwise operations on these bit vectors. So the algorithm does not support long reads whose lengths are on the order of thousands to millions of base pairs these days. So these are the algorithmic limitations of the BiTAP algorithm. And even after we solve the algorithmic limitations, we find that we cannot extract significant performance benefits with algorithmic enhancements alone. For example, while BiTAP iterates over each character of the input text sequentially, we can enable text-level parallelism to improve its performance. However, the achievable level of parallelism is limited by the number of compute units in existing systems like CPUs. So we would expect that a GPU, which has thousands of compute units, can overcome the limited compute parallelism issues that CPUs experience. However, we find that a GPU implementation of the BiTAP algorithm suffers from the limited amount of memory bandwidth available for each GPU thread. And these are the hardware-related limitations. So in order to overcome these limitations and design an efficient accelerator, we find that we need to both modify and extend the BiTAP algorithm and also develop specialized hardware that can exploit the new opportunities that our algorithmic modifications provide. To this end, we propose GenASM. So to our knowledge, GenASM is the first ASM acceleration framework for genome sequence analysis, and it is also first that enhances and accelerates BiTAP. So we make significant modifications to BiTAP in order to overcome those 5 limitations. First, we modify the BiTAP algorithm by extending it to support long reads and by eliminating loop carry data dependencies to enable parallelization. Second, we develop a novel BiTAP-compatible algorithm for traceback, which uses information collected during ASM about the different types of errors to identify the optimal alignment of reads. And these cover the algorithmic contributions of GenASM. Third, we co-design specialized low power and area efficient hardware for both algorithms, and this covers the hardware level contribution of GenASM. Let's look at the hardware design of GenASM. So our co-designed hardware consists of 2 components. First, GenASM DC, which provides hardware support to efficiently execute our GenASM DC algorithm, which performs distance calculation. And second, GenASM TB, which provides hardware support to efficiently execute our novel GenASM TB algorithm that performs traceback and finds the optimal alignment. GenASM also has 2 types of SRAM buffers, DC SRAM and TB SRAMs. Let's look at the high-level overview of GenASM. So GenASM execution starts when the host CPU issues a task to GenASM with the reference and the query sequences locations. And then GenASM DC reads the corresponding reference text region and the query pattern from the memory, and then writes these to its dedicated SRAM, DC SRAM. In GenASM, in order to decrease the memory footprint of the algorithm, we follow a divide and conquer approach where we divide the text and pattern into overlapping windows and perform the traceback computation for each window. And after all of the windows' partial traceback outputs are generated, we merge them to find the complete traceback output. So as a next step, GenASM DC divides the reference text and query pattern into multiple overlapping windows. And for each subtext and subpattern, GenASM DC searches for the subpattern within the subtext and generates the bit vectors. And then GenASM DC writes these bit vectors to TB SRAMs. And once GenASM DC completes its search and bit vector generation for the current window, then GenASM TB starts reading the stored bit vectors from TB SRAMs and generates the Windows traceback output. And once GenASM TB generates this output, GenASM computes the next window and repeats from steps 3 to 7 until all windows are completed. Our specialized compute units and on-chip SRAMs help us to match the rate of computation with memory capacity and bandwidth, achieve high performance and power efficiency, and also scale linearly in performance with the number of parallel compute units that we add to the system. Let's look at GenASM DC's hardware design. So we implement GenASM DC as a linear cyclic systolic array-based accelerator using small and very simple logic components. And this design helps us to maximize parallelism and minimize memory bandwidth and memory footprint. So processing core, or PC, is the basic compute component which computes the intermediate bit vectors, which is basically one inner loop iteration. And when we add the flip-flop based storage logic around the processing core, we define a processing element, or PE. And multiple PEs are concatenated to define a processing block. So we have DC SRAM, which stores the reference text, the pattern bit mask for the query read, and any intermediate data generated from PEs. And we also have TB SRAMs, which store the intermediate bit vectors generated by each PE of GenASM DC for later use by GenASM TB. And we implement GenASM TB hardware using very simple logic, which first reads the bit vectors from one of the TB SRAMs using the computed address, and then performs the required bitwise comparisons to find the traceback output for the current position. And third, computes the next TB SRAM address to read the new set of bit vectors. After GenASM TB finds the complete traceback output, or in other words, cigar string, it writes the output to main memory and completes its execution. So we demonstrate the efficiency and flexibility of the GenASM acceleration framework by describing 3 use cases of approximate string matching in genome sequence analysis. First, read alignment step of short and long read mapping. Second, pre-alignment filtering for short reads. And third, edit distance calculation between any 2 arbitrary length sequences. And we believe the GenASM framework can be useful for many other use cases, and we discuss some of them briefly in our paper, for example, including generic text search. Let's look at our evaluation of the GenASM design and framework. So we evaluate GenASM using a combination of synthesis of our DC and TB accelerator data paths and a detailed simulation-based performance modeling. And we evaluate a 16 gigabytes of HMC-like 3D stacked DRAM architecture with 32 volts. So our accelerators can be ported anywhere in the system, but in order to achieve high parallelism and low power consumption, we place both DC and TB in the logic layer of 3D stacked memory. And for the use cases we evaluate, we compare GenASM with state-of-the-art software and hardware baselines. So I won't go into details, but you can refer to our paper for more details on the evaluation methodology for each specific use case. Let's look at our key results, starting with area and power numbers. So as I said, we synthesize our DC and TB accelerator data paths, and when both accelerators operate at 1 gigahertz, we find that for 32 GenASM accelerators, where we have 1 for each HMC volt, total area overhead is 10.69 millimeters square, and total power consumption is 3.23 watts. So we observe that both area and power consumption of GenASM at a single volt is around 1% of the area and power consumption of a single Xeon CPU core, which means that GenASM has low area and power overheads. Let's look at our results for the first use case, which is read alignment. So as software baselines, we compare GenASM with BWA-MAM, which is shown with red bars, and Minimap2, which is shown with purple bars. And both are, as we know, commonly used state-of-the-art read mappers. We find that GenASM achieves 648 times speed up over BWA-MAM and 116 times speed up over Minimap2, while reducing power consumption by 34 times and 37 times, respectively. And compared to Gagtov-Darwin, which is a state-of-the-art long-read alignment accelerator, GenASM provides 3.9 times better throughput, 6.6 times better throughput per unit area, and 10.5 times better throughput per unit power. And for short reads compared to same software baselines, GenASM provides significant speed up and reduction in power consumption, similar to long reads. And compared to ScyllaX of GenX, which is a state-of-the-art short-read alignment accelerator, GenASM provides 1.9 times better throughput while using significantly less logic area and logic power. Let's look at our results for the second use case, pre-alignment filtering. So I don't have time to cover this result in detail, but here is the key takeaway. Compared to SUJI, which is a state-of-the-art FPGA-based filter, GenASM is more efficient in terms of both speed and power consumption, while significantly improving the accuracy of pre-alignment filtering. And for our third use case, edit distance calculation, again, I won't be able to cover the details, but compared to the software baseline, EDLib, GenASM provides 2 to 4 orders of magnitude speed up while reducing power consumption by 2 orders of magnitude. And compared to the hardware baseline ASAP, again, GenASM provides significant speed up while consuming significantly less power. Before I conclude, here is a list of additional details that you can find in our paper. So to conclude, in this work, we focus on approximate string matching because it is one of the main bottlenecks of genome sequence analysis, and we propose GenASM, an approximate string matching acceleration framework, to accelerate multiple steps of genome sequence analysis. And GenASM is the first work that enhances and accelerates BiTAP for ASM with genomic sequences. And in GenASM, we co-design our modified, scalable, and memory-efficient algorithms with low power and area-efficient hardware accelerators. And we evaluate 3 different use cases and show that GenASM is significantly more efficient for all the 3 use cases in terms of throughput and throughput per unit power than state-of-the-art software and hardware baselines. So you can refer to our paper for more details. And we also release the software implementation of both DC and TB algorithms in our GitHub page, which you can find the link here. And before I finish my talk, I also want to mention to one of our more recent papers, SIGRAM, which is published at ISCA this year. And in SIGRAM, we build upon GenASM to provide the first universal genomic mapping accelerator that can support both sequence-to-graph mapping and sequence-to-sequence mapping. And in SIGRAM, for the seeding part, we have a minimizer-based seeding algorithm, and we also develop a novel bit vector-based sequence-to-graph alignment algorithm, and we co-design efficient hardware accelerators for both algorithms. And we will be releasing our software implementation and the data sets we use in our GitHub page soon for SIGRAM as well. Thank you so much.
Thank you. Thank you for a very good talk. Questions, but I think it's great that we're looking into accelerators as we increase throughput, and in particular, that are power efficient since all our calculations use so much power. I'm just curious about your hardware implementation. Is it something that you manufacture for your project? Do you think that could be scaled by some third party?
By somewhat, sorry.
But your hardware, I imagine you guys did it yourself. Is this something that could be commercialized?
So that's a really good question. As you can see from this title page, this work was in collaboration with Intel. So we are in the phase for the GenASM work that we can release our implementation, which can be mapped to FPGAs and can be run by anyone, basically.
Okay, FPGAs, that's a good answer. Okay, so we got potentially running FPGAs, clouds, and things like that. Thank you.
Exactly.